Hello everybody, welcome to this video about solids of revolution. We're going to begin this video with a video. Before we get started about talking about solids of revolution, I wanted to present an animation that shows you how we create solids of revolution, just so that we have in our mind what we're looking at, because being able to visualize these things is like one of the most important parts of it. Okay, so let's see if this works. Okay, good. So here we have the function y equals the square root of x, and we are going to choose a portion of it. And then this other line here, y equals 1/10 x, and then we're going to cut off a region at x equals 4. So there is a, can I color on this? Oh yeah, so this shaded region, we're now going to spin around. We're going to rotate it around the x-axis like this, and it's going to create a solid shape. So let's see if we can get it to go. Oh, I've made it start over. Alas. So in all the problems we're going to be looking at here, we're going to start by bounding a region in the plane, like the video is doing here, identifying that region, and then we're going to rotate it around a line, either a horizontal or vertical line. So here, we're going to rotate this region around the x-axis. Whoa! And it's going to create a shape that looks like this. So the way we're going to find the volume of these is very similar to the idea of cross-sections that we did before. But here, since we created these shapes by rotation, the cross-sections are always going to be based on circles. So we're really only going to be focusing on circular shapes. So this particular shape has cross-sections that look like donuts, so that's just a big circle minus a little circle, and we'll learn how to deal with that. Okay, so let's see. I want to go back to PowerPoint. This guy. I'll open it. Okay. Alright, so we just watched this video. So here again is the graph of y equals square root of x. Here I've bound my region in between 0 and 8. So here's the region of rotation. And I want to rotate around the x-axis. So this is going to create a shape that's similar to the one we just saw in the video, but it won't have there'll be circular cross-sections, not donut ones. Okay, so if I want to figure out the volume of this shape, when I rotate it, I'm going to get cross-sections that look like circles. The radius of each cross-section is going to be square root of x, because that is the distance from the x-axis up to the top of this region. And the area of each of these cross-sections is just going to follow the area of a circle, pi r squared, and in this case, r is going to be the square root of x. So, all right. And we want to add up these cross sections all the way from 0 to 8. So our bounds of integration are going to be from 0 to 8. Like so. And when we punch that into the calculator, we get that the volume is 32 pi cubic units. That's how that works. It's similar to the example problem we saw before when we were doing cross-sections, where we had circular cross-sections. Let's take a look at another example. So this time we're going to use the same region. So we're still going to use this region that's bounded here. But instead of rotating it around the x-axis, we're going to rotate it around the line y equals -1. So this is going to be our axis of rotation. So the way you want to think about this is that we're going to rotate this whole region from -1 all the way up to root x, and then subtract out this little piece here because this, the green zone is not in the shaded region that we're trying to rotate. So we're going to figure out the volume of the solid that would result if we spun the blue region around, and then subtract out that center section created by the green region, and that will leave us with the volume of the solid that only came from the red region. So let's take a second and think about the radii of the cross sections that we are going to be creating here. Okay, so if we think about the radius of a cross section of this blue region, so that's a representative radius there. What is this distance? Well, it's 1. We know that in order to get from -1 up to the axis, we go 1 unit. And then in addition to that, we're going to go up by square root of x. That's how much this distance is. So the outer radius, so the larger radius, is 1 plus the square root of x. So if we were going to find the volume that is generated from rotating the blue region, that would be the integral from 0 to 8 of pi times 1 plus root x squared. So that's pi r squared here, where the radius is 1 plus square root of x. So that would be the outer shape. And then the part that we would want to subtract out is the volume of the solid to be generated by rotating this green region. So the green region is easy to find the volume of because its radius doesn't change at all. The radius of this region is always 1. So we would want to integrate from 0 to 8 again, but this time the radius is always 1. It doesn't change. And so the red region, the red volume that we are looking for, would be the volume of the big shape minus the volume of the little shape. And so you can put that in your calculator and figure out what that volume would be. We can rewrite this as a single integral because the bounds on both integrals are the same. So another way to write this would be, we can pull a pi out because it's just a constant. All right, so this is the big radius squared minus the square of the little radius. By far the most common mistake that people make on this type of problem is that you subtract the two radii and then square. So people look at this, are like, okay, the outer radius is 1 plus root x, the inner radius is 1. I'm going to take the difference of those two radii, I get root x, and I square it, and that's it. So you can't do that because what you have to remember is that you are subtracting areas here. The area of like a big circle, so our outer circle was in red. If this is a cross section of that shape, it would look something like this. And then we're subtracting the area of like the green center in here. So we are trying to subtract the green area from the red area, not the green radius from the red radius. And if you're going to subtract areas, you have to square the radii first before you subtract. So long story short, when you combine this into a single integral, it needs to be the big radius squared minus a small radius squared, not big radius minus small radius quantity squared, because of order of operations, everything I just said. So let's look at this example. Okay, so here the region of rotation is in Chiro. It's bounded by these two functions. So we are going to rotate this around the x-axis. So our axis of rotation is here. So we're going to get like a funky bowl shape. So first things we want to do are find the bounds of integration. From looking at this graph, I can see that I'm going to want to integrate from 0 to 4 because that's clearly labeled on this graph. But go ahead and figure it out algebraically. Okay, I went ahead and solved this equation. I got the bounds of integration are from 0 to 4, which is what it says on the graph, so that's good. Okay, so the next thing we want to do is to think about what is the big radius going to be, so the red radius, and what is the area of one of its cross-sections going to be, and then what is the small radius going to be, and what's the area of one of its cross-sections going to be. So we are trying to fill in this integral from 0 to 4 of big cross-section area minus small cross-section area. Okay, so go ahead and try to fill in the first part. What is an expression for the area of one of the red cross-sections? Okay, the red graph is f of x, so if the radius is 2 root x, the area of that cross-section would be pi times 2 root x squared. Okay, go ahead and fill in the small cross-section area. All right, so the radius of the small cross-section is just 1/4 x squared, which means that the area is pi times 1/4 x squared. So you can put that in your calculator. We can pull out a pi, because it's a constant and there's one on each term. You have 2 root x squared minus 1/4 x squared. So again, we're taking the difference of the squared radii, not taking the difference between the radii and then squaring them. So go ahead and pop this in your calculator and see what answer you get. Okay, when I put this in my calculator, I got that the volume is 60.32 cubic units. All right. Okay, so we already did this. Okay, so we want, the next problem asks us to find the volume when we rotate around a vertical line, x equals 5. So our axis of rotation is going to be here. And in order to do this, we're going to want to integrate with respect to y. Okay, so I'm going to go ahead and set this up and then explain it as I go. Okay, so this is a tougher volume question. I'm going to just try to talk this. We'll go over it in class, but there's not much time left on this video, so just follow what you can, and then we'll talk about it more in class. Okay, so since we are rotating around a vertical line, we're going to need to integrate with respect to y, which means that we need to solve the given equations for x. So we get x equals y squared over 4 for the red graph, and x equals 2 root y for the blue graph. So that means that the distance between the y-axis and that graph is given by these two equations we just solved for. So on the graph, I've marked the total distance from the axis, from the y-axis to our axis of rotation is 5 units, because we're rotating around the line x equals 5. So that means that the larger radius for our cross-section from our axis of rotation out to the red graph is going to be 5 minus y squared over 4. Because we know the distance from the y-axis to the graph is y squared over 4, so the remaining distance must be 5 minus that. Ditto for the small radius. The total distance from the y-axis over there is 5. We know that the horizontal distance from the y-axis to the blue graph is 2 root y. So that means that the inner radius here has to be 5 minus 2 root y. And so when we plug those in to our volume integral, we are integrating from 0 to 4. So we're integrating along the y-axis. The big cross-section is going to be, so that's the red one, is 5 minus y squared over 4 squared, because the area of a circle is pi r squared. And then the small area is going to be 5 minus 2 root y squared, again, because the area of a circle is pi r squared. So when you put that in your calculator, you should get an answer. Let's see what we get. That's to get 107.23 cubic units. But again, we'll talk more about this example in class. But that's a good warm-up for